All right. Well, welcome to How Moisture Gets into Buildings with Chris Dawkins. I'm Rick Gardner with IBEC. We're going to be giving you a little bit of an introduction into some of the important concepts that will be discussed at the Building Enclosure Symposium, as well as just an introduction to the building enclosure. So I'm going to, at this point, introduce Chris Dawkins. Chris, you want to wave so everybody knows?
Sure.
Okay. Chris is IBEC's secretary and treasurer right now, and he'll be moving up to one of the vice presidencies here in March, right? And then he's currently a partner in Beech Consulting Incorporated just outside of Atlanta. He's a professional engineer. He started out his career with the U.S. Navy Civil Engineers Corps, where he was there for 12 years. And then he started in a small company that became a huge company called Kimley and Horn and Associates. He was there for 10 years. Then he split off with a friend and started Beech Consulting. He's been a very active member of the Georgia chapter, as well as a leader in the Georgia chapter. He talks about his role as being a facility engineer for many of his clients, doing assessments for insurance carriers, acting as a third party to help contractors get the buildings right for their clients. And a lot of his work is mostly commercial, but he does dabble with residential. So on that, introduce to you Chris Dawkins.
Hey, it's great to be with y'all. You can hear me, right? Everybody hear me? Good. Okay, good. And Rick's going to put up the PowerPoint on the screen. And, this was just, I'm looking at a 51-inch screen right here, guys. So I've got you on two screens. So I might look up at the big screen. Can you put up the PowerPoint, Rick?
Yep.
Sweet. Okay. And then take it to show. There we go. So my partner and I developed this a while back. We give this to aspiring industrial hygienists about once a quarter at another facility. So we can go ahead, Rick. So how does water get in? We're going to release is easy. That's plumbing leaks or floods. I didn't put floods in there, but if a plumbing system breaks, a sprinkler head breaks, or you have some kind of plumbing leak in a building, that causes all kinds of water problems. And some of the principles we cover here, like diffusion and some of that kind of thing, are they come into play. But we're not going to talk about release. We're really going to talk about intrusion, and that's situations with the enclosure, or others call it the envelope. We call it both. Surface water we're not going to cover either, because if a building floods, it's similar to a plumbing leak. We're really going to talk about the envelope problems. And then, of course, we call that bulk water. And then airflow vapor drive is moisture vapor. So that's another big way water gets into buildings, and we're going to discuss that as we go forward. You can click on, Rick. This is just go ahead and click. That's a release. You have a leak around the plumbing drain. Bingo. Something in the ceiling below. So that's your last release photo. Let's go ahead. So fundamentals. Gravity always prevails. And don't forget about water being able to, if you get water like about an inch of water on the floor, it can wick up the wall. Or if you have a surface water problem outside, say the surface grade is a couple inches above the floor slab, then that can basically create a wicking kind of issue. We see that sometimes, at ground floors of buildings. Wind-driven rain can basically flow uphill or up a wall. You can remember this: a 50-mile-an-hour wind. This is physics. A 50-mile-an-hour wind will blow water up a wall 2 inches. So if you don't have a good coping cover, you've got a big problem. So anyway, that's very important. The building code has us designing to 90 miles an hour. So think about a 90, and I'm dealing with building science students, so you guys know what log curves are. A 90-mile-an-hour wind is going to blow up the wall maybe 3.5 inches. It's not linear. Debris within any kind of drainage assembly is a dam, and that causes problems. If you back water up onto a roof, it's gonna be a problem. And then lastly, slow drainage always is a problem too. You want to get water off of a roof assembly as fast as possible. So let's keep going. So we're going to talk a little bit about shingle roofs. I don't think I've got clay tile, slate, or wood shake in this setup, but they're basically, the industry calls them steep slope roofs, and then flat roofs they call low slope roofs. And when you're at the BES, you're going to hear about, you're going to hear about what's listed below. You guys can screenshot this too, you know. Modified bitumen built up is getting rarer and rarer, although some clients still love it. It's actually one of the best roofing systems out there, but since it's so dependent on oil, and as oil's gone up, it's gotten less and less prevalent. It used to be everywhere. Modified bit is also essentially a oil-based product. A lot of institutional colleges, schools, and some commercial love modified bit. Single ply is what you see a lot of these days. That's, yeah, I've got them listed there. You back up EPDM, PVC, and TPO systems. You'll see once in a while, you see a spray polyurethane foam. It's a great roof. It creates an exterior insulation. It's both the roof barrier and it's also an exterior insulation, excellent. And then of course, metal. You've got both R panels, which are the ribbed panels you see often on metal assemblies with exposed fasteners. And then of course, standing seam systems, which are typically cover all the fasteners. So that's you might hear about some of those terms when you're at BES. So let's roll. I think we're going to talk. Yeah, you need to understand these two terms too. Base flashing is, I'm going to show you some pictures of some base flashing in a second. That's where the, say on a low slope roof, that's going to be where the roof itself turns up a parapet wall or onto a wall, onto an adjacent wall, and sometimes that base flashing is a different material than the roof, so it's shingle lapped. The low slope roof goes under the base flashing, and then there's metal step flashings that are integrated. A metal step flashing is really more of a residential. You'll see some photos of that in a minute. Cap flashing is what's over the top of a parapet wall, so just basically an upside down U, for lack of a better term. So let's keep rolling. These are some of what I'm telling you is things you might hear somebody say in a lecture at BES. So we're talking briefly about shingle failures, how shingles fail. I don't think I've got any. We're going to talk about these from photos in a minute, so I'm not going to waste a lot of time on this other than ice dams. If you're in a northern climate, you can get ice dams that are caused by the differential temperature at the roof edge and snow melt. And basically you'll get some ice at the roof edge that will create a dam, and then the water will back up, say a roof valley, and then, migrate into the roof assembly and cause lots of trouble. So you have that in the northern areas. Here in Georgia, where I am, we have what we call pine needle dams. They act just exactly like ice dams, except they're not related to temperature. So let's keep on rolling. This is the typical, apartment building's roof, and every vent you see there is a potential leakage source. Every roof valley, if it's not flashed correctly, is a potential leak source. Once in a blue moon, you'll get leaks in the field areas. It takes a really incompetent roofer to create leaks in the field area, but on occasion you'll find it, but not often. Usually it's typically your vents and your valleys, which I'm showing you there. We can keep going, Rick. This is a side wall I was talking about that a second ago. This is where the step flashing would be. I've got a picture coming up in a minute, but this is a typical sidewall at a roof. You've got step flashing that turns over. There's a building wrap under these shingles, right? So the step flashing comes out on the horizontally onto that wrap that's under the shingles, and then turns up behind the wrap behind the sidewall. The one thing that's in this photo that we get away with here in Georgia that you could never get away with in the north is you can see how close that sideboard is to the shingles. If you do that up north, you'll get debris stuck in that little tiny opening. It'll cause a dam of water, which will freeze and then expand and break that siding off. So we get away with things in Georgia that you can't get away with up north. That's probably enough on that. This is showing you how the step flashing works right here. And I actually misspoke. You see the vertical leg of the flashing in the upper left corner there is tied up under the building wrap behind the cladding. Cladding is whatever's on the wall: brick, siding, stucco, panels, ... Behind that is that, you see that gray colored piece, that's the building wrap that's behind it. That flashing turns up under that and then laps over and onto individual shingles going up the wall. You can kind of follow the pattern as you go from top left to top right to bottom. But that's step flashing. Raise your hands if this is the first time you've heard any of these terms. Okay, well, that's good. Y'all are knowledgeable. Good. Okay, let's keep going. So this next photo, you see the step flashing up high, okay, uphill, and then you see the diverter flashing at the bottom. The roof industry calls this diverter flashing a kick out. And you see this happens to be on a shingle roof, but you've got to have this same concept on commercial structures too. Anywhere you've got a side wall where you dump water into, say, a gutter system, you've got to have a kick out, or the water will basically run. You can see where the arrow says kick out diverter. If you don't have that kick out diverter there and you just bring the step flashing straight down basically straight down to the roof edge, water has a tendency to run right in the hole. There's no way to fill that hole. So basically you need that diverter. This is a big deal. It's a big deal, especially in residential, but I've seen it in commercial over and over again also. It's just not as, it's not as well known in the commercial, and there's a lot of places where a commercial doesn't have this. But if you have it, got a sidewall and a roof edge that meet, you got to have that diverter. You guys learning this now is going to save your clients a ton of money. Y'all are all new to the industry. I've been in it a long time, and I can't tell you how many times this is a problem. Even I've been doing this 25 years and it's still a problem today. We just have a lot of folks that don't get bulk water problems. I think that's enough on that one. We talked a little bit about valleys a minute ago. You can see the valley in the far away area and the valley here. So when we happened to be walking these roofs, we were going, hey, looks like they've had some leakage problems before manifested by valley repairs. I think that's enough on that one. And this is why if you follow this, you guys can screenshot this all day long. There's some pretty nice details in here. So if you properly treat the valley with a valley flashing as shown in these two views, you won't have to do what was on the photo before. What they had to do was pull the shingles back, integrate a valley flashing like the yellow or the red, in the top or bottom photos, and then put that back in, and then weave those shingles back together again. That's why those repairs were done. So there's various materials out there, Weather Watch and several others that are very easy for roofers to put into a valley. If you don't do it, you'll get leaks. So I think that's enough there. This is a residential or a shingle setup, but this is another. But this can happen on commercial roofs. So I want you to understand these concepts, not worry about whether it's shingle or commercial. But the top left photo is definitely a residential / shingle issue. And that's that you see that flange, you've got a 5-in-1 tool stuck up under the flange. And if you take a look, the shingle layer right above where that 5-in-1 tool is stuck under, come down one course, Rick, come down one. There you go, right there. That shingle should be lapped over that side of that flange, because if we get a wind-driven rain blowing in the direction of that, left to right, it can blow right under that flange, and then there's a hole right there for the vent in the deck. So that's a hole in the roof. So this is basics. I'm giving you some roofing basics. And then of course the lower photo, I think, is probably just showing you the obvious, right? The roof boots, that's called a boot that goes around the vent. Those boots have a life of about 10 years. So if you let it go 15, it'll look like that, and that's a hole in the roof. So sometimes you'll have a leak. This is kind of interesting. Sometimes you have a leak at the first story of an apartment building or a home that's maybe 3 stories high. And they say, I'm getting water in this wall in my bathroom or in my washer dryer room, anywhere there's plumbing fixtures, in the kitchen. Because basically what they do is they take this vent pipe and get it to a wall, and they take it in a chase right up through the wall and up into the attic and through the roof. And it's so interesting. You go, well, let's go up on the roof and take a look at those vent boots, and bingo. So anyway, I think enough on that. And then let's not spend any time on this, but if you ever guys want to roof your own house, here's a good step-by-step methodology of how to install a vent boot. So that's how you should do it right. Drip edge flashing is very important. This happens to be for a steep slope assembly, but the drip edge, you have a drip edge on all commercial roofs. It's very similar. Anytime you have a flat roof, you'll have a drip edge assembly that's very similar to this in concept. This is showing you how to integrate that drip edge along the rake. The rake is the left side of this photo. That'd be the sidewall of the that's the rake. And can you tell that's the slope that's going up the slope on the sidewall, and then the lower edge is it says edge at eave. People use those terms interchangeably. So you got a drip edge. I usually call that the edge of a roof, and a lot of folks call it the eave, which is the left to right lower edge of a roof slope. So that helps you understand. If you don't have a drip edge, another place water is going to blow up under the deck and into the building below. So we keep going. Low slope. I think we're going to cover a lot of this. You can screenshot that and look at it later. We're going to cover this with some photos. So this is a low slope roof. It happens to be a gravel ballasted modified bit roof. You can see the field. It's got field drains. It looks like if it overflowed. I don't see overflow drains in this photo, but it could be that one of those is an overflow and one's a drain. But I like this picture because it shows a typical condition of a low slope roof with gravel ballast. You see a base flashing there on the right where it's hitting the wall. But you see that big hole in the wall beside the door. I bet Rick can find it. Yeah, bingo. or if those louvers are not flashed right, or if that door threshold is not flashed right, or if that light fixture is not flashed right in the wall, you can get essentially a leak that looks like a roof leak. It's really a wall leak above that roof. I've been in cases where I looked at an assembly about 10 years ago in Nashville, Tennessee. It was 16. It was like a wedding cake building. And they said, we've only got leaks at two of the layers of the wedding cake. And went up there, and sure enough, they had leaks in their walls right above that location, but nothing on the roof. And I said, we're chasing the wrong thing, because they were angry with their roofer, and it was the walls letting water come into under the roof deck at the wall. So anyway, that gives you a little view. I said a modified bit. This modified bit at the base flashings there at the wall, this is a built-up roof in the main field, but you can't tell that because it's covered with rock ballast. So let's keep going. That's a typical base flashing right there. The stucco wall right at the very top, and then a metal flashing under this, hopefully integrated properly with the building wrap that would be behind the stucco, and then that falling on top of that's modified bit. Cap sheet right there. That's then the base flashing, that's turning vertically up the wall. And then that looks like that's tying into a built up there at the base. So you're getting to see two different kinds of roofing. And I just wanted you to understand what a base flashing is. Let's keep going. That's ponding on a roof is never good. Even low slope roofs should drain. So if you see ponding, it might not be a problem, but it's going to be a problem down the road if a weld, say we're on a TPO or a EPDM or a PVC roof, you've got welded seams under that pond. At this built up, you've got lap joints with tar, so ponding's not your friend. That can be fixed with crickets and sloped insulation. Anyway. I'm showing you problems, not perfect details for how to do all this right. Plugged roof drain, big problem. Might have been the reason for the ponding here. Let's keep going. That's a maintenance issue. This is another maintenance issue. Either a hole from a pipe vent, or who knows what this is. I don't know. You can tell by the degradation around the inside of the hole. It's been there a while. So that doesn't happen every day on roofs, but I've seen it before. This is a photo of a roof at a hotel in Augusta, Georgia. And if you can go down there, Rick, to the base flashing, so you see the top of you see the top of the membrane just stops right at the vertical edge. This little vent was blown off during a windstorm. But I love the picture. When I saw it, I took it for a lot of reasons. One is you can see the base flashing should have been wrapped into that hole or into that opening, not just stop at the vertical edge. And then you can see the electrical hole, the hole for the electrical line right there was probably letting wind-driven rain blow in that hole and just run down behind that vertical edge. So that's how not to do a curb. You see curbs on roofs on low slope roofs all the time. So it's a pretty instructive photo, how not to do things and why they leak when there's no, not a blow off like this one. This one leaked terribly after that vent cover blew off. But we can keep going. This is a scupper on the left and a field drain on the right. The scupper's there for emergency drainage. But if you think about it, that scupper has got to be integrated properly with the roof that's to the right. And then it's got to be properly integrated with the waterproofing on the wall assembly on the other side. And that's a huge leakage source in buildings over and over again. You can also see a little ponding going on. there, and you can see the welded seams this is, I believe this is a TPO. It's really difficult to tell PVC or TPO from this distance apart, but you see the welded seam about where that black arrow is. So anyway, let's keep going. This is just showing you more ponding and welded. You can see the welded seams of the single membrane roof here. So if any of those seams have a hole in them, a little pinhole or something, that's going to let water in. So how water gets in. Now we're going to talk a little bit about this. Is, you guys will probably, you may already have some of these. This is a wet wall detector. It's a leak seeker. It's made by Delmhorst. I use something similar, but the key to these instruments is they're fantastic tools, but you must have some knowledge of what you're checking under them. I think the best war story is I use wall meters like this sometimes on interior walls in facilities where we're chasing mold or chasing a water leak in walls. I'm just getting over bronchitis, y'all, but I'm gonna make it through this. But we were checking walls, and an associate consultant was walking around the room with a meter similar to this, and getting high readings. And I was like, there's nothing wrong with those walls. We had problems on the exterior wall at this particular location, but not on interior walls. So we popped off. We had the ability to take some things off. We did. We took off the wallpaper that was on the wall, and the wallpaper glue was conductive. These are induction-based meters. They send an electrical circuit through the whatever you're putting them on, and then if they pick up, they basically with the induction will pick up water. But you got to know. So the glue of that wallpaper was conductive like water, so it looked like water, but it wasn't. We pulled the wallpaper off, put the meter on the gypsum wallboard, and the meter went to zero. So you got to be careful with. They're great meters, but my driving point to you as new building scientists is you must have done some cuts, or you must know what's under them. You can get a lot of false positives with meters like this. So I think that's enough. This happens to be a guy taking an infrared camera. We're at sort of that same roof. You can see the base flashings. You can see some of the built up. You can see he's got an infrared camera in his hand. You go to the next photo, and you see an infrared photo. This is old technology, man. I got to get some newer photos. I just bought a new infrared about 6 months ago. But anyway, the same applies to infrared. You've got to know a little bit about what you're looking at, or you'll get false positives. And I'm guessing if you guys are in building science, you know that there's certain times of the day, the heat of the day is not the time to use an IR camera. You want to do IR typically at night when it's cooler, so you haven't got thermal, radiation. Basically, you can get a lot of false positives if you don't do infrared at the right times. So anyway, that's enough of that. Walls, this is good. I think this next slide is one of my favorite slides. It's why building scientists exist. And in this basically, if you're going to screenshot this one. 1800s to around 1900 or so, buildings weren't tall. They were, 3 or 4 stories maybe, and lower, of course. But the left photo is a mass masonry wall, and that was pretty typical. And you might have a plaster on it, and you might not. But let's not get too caught up into details. But the concept of the mass masonry wall was the water would get into the exterior and then evaporate back out. nobody was worried really about water getting to the interior. I guess if you had a 10-day rain in a situation like that, it might finally get in, but typically just the wall assembly, the word wythe, does that make sense to y'all? You shake your heads. W-Y-T-H-E, wythe. That's a layer of brick. So I just looked at a building in San Francisco about 2 years ago. It was a 5-wythe wall. So it was about 16 inches. It was built in 1912. And we were helping the owner take the plaster off and not put it back and repoint the wall because the plaster had not been put on right. And it was basically holding water against the brick and also cracking terribly because it wasn't jointed properly when it was put on. So it was a 5-wythe assembly, 5 wythes of brick. So anyway, so then you go to a little later. We started shrinking the number of wythes. You got to see that's a 2-wythe wall with a stone on the inside. But I've seen many just 2-wythe, 3-wythe type brick assemblies. Basically, the reason for this is there's probably a structure. The mass masonry wall on the left was the structure and the barrier. When I say barrier, and the water shedder. The one on the left has an internal structure, so the walls got smaller. And then as we've gone to the present day, typically we have a superstructure with, say steel or mix of steel superstructure with concrete slabs and an infill wall. And you see basically we got metal studs and then a little wall cladding on the outside. So this is a pretty good photo. I was looking at it backwards. I'm sorry, I got messed up with that plaster a second ago. That plaster's on the interior side of the wall in the first two. I guess I got messed up because of that job I did in San Francisco. But the principles are all the same. So basically you got a cladding here on the outside. And again, I don't want you to get hung up on stone veneer. That could be brick. That could be stucco. It could be thin brick. It could be some kind of siding material. It could be panels. It could be anything. But fundamentally then behind it's typically an airspace. Typically behind that is some kind of wall sheathing, then studs, insulated cavity, and then an interior drywall. So, so you can see how close the water now is to the interior. And so without proper waterproofing of that wall sheathing that's right behind the airspace, we have big problems. And that's why building scientists are in business today. So we can keep going. I think I've covered a lot of that already, but this is kind of worth going through. There's less mass. Think about that photo on the left, or the wall on the left. It's got a ton of mass, so it's like a fantastic sponge. Well, you go to the cavity wall that all of us are dealing with today. There's hardly anything. The sponge is just way smaller, so therefore it can't absorb that much water before you got what we call bulk water getting to the airspace. We'll cover the rest as we go, because this talk's a little longer than 45 minutes. How are we doing on time, by the way? Okay, so bulk water, liquid water, that's a big deal. Air infiltration, we're going to talk about. Those are your two main sources. What I want you to understand about vapor diffusion is this. It's moisture migration through a material. Okay. So bulk water is just like pouring a glass of water into the airspace. It's liquid water. That's what the industry likes to call it, bulk water. And I'll often call it free water. Air infiltration is going to be moisture carried by air through an opening in your wall that should have an air barrier to stop it. And then diffusion is if a material gets wet on one side that moisture will migrate very slowly through that material. That's what diffusion is. We're not going to spend a lot of time on it, but where diffusion is a problem is, say you've got a gypsum wall board or some kind of wood-based wall sheathing, which should never see water, and it should not see moisture borne by air if it's got a good air barrier on it. But if you don't have one of those and you get moisture into that sheathing material, now it's going to diffuse through the material to the interior. And while it's diffusing or evaporating, it could be evaporating to the exterior or diffusing to the interior, and then evaporating once it gets to the other side of the interior. While it's inside that material, if that material is not water resistant, it might be damaging that material. All right. Hopefully you got it. Usually I can talk to you and go, got it. These are typical component names. Weather resistant barrier is basically the barrier over the wall sheathing. The drainage space is the air space. The drainage plane is the surface of the WRB. Flashing, we've talked about a little bit. We talked about roofing a minute ago. That's typically a metal material, or it could be a fluid applied material, but that's in the next lecture. It basically directs the water, from the drainage plane and then to either another WRB or to the exterior. And of course, the flashing's got to be shingle lapped behind whatever's upstream of it, right? A lot of time, it's sometimes what we do is so simple. I get to a job and go, well, why do we have water in the ceiling here? And we start opening brick and go, well, they put an L flashing, at the floor above and just reverse lap it. They just push the vertical leg of that L flashing against the wallpaper and put a little caulk at the top, and bingo, water drips, comes behind the flashing and is in the building. Air barrier, a lot of times, how many folks, raise your hands, are from the north? Okay, well, okay, I see one. Air barrier is going to be, a lot of times here in the Southeast, the WRB is handling both water, bulk water, and air. As you work your way through different climate zones, you may have a separate air barrier and possibly a separate vapor retarder, further inside the wall. But this gets into lectures, about 3 lectures from this. But when you're at BES, you'll get some of this, which will be great. So let's keep going. So this happens to be a wall that has the WRB. This is a brick wall. And again, I don't want you to get stuck on the flashing concepts are identical regardless of the cladding. So this happens to be brick, but as I said too many times before already, don't get hung up on the cladding. That's just, the cladding is what's on the exterior. But you can see you've got an air barrier, and WRB is pointing at the same thing. See the air barrier is, and they're using the concept of a 30-pound felt paper, which is used to this day, but a lot of times we'll have Tyvek or other things. And then there's a multitude of fluid applieds. If you want to look up one, I'm familiar with, is Exo Air. You can look up as a fluid applied that goes on. But then you can see the flashing at the base of the wall. You see a weep hole in the brick. That could be a weep assembly in stucco. That could be another weep assembly in some kind of panel or siding wall. But you see how that turns up behind the air barrier, and then that's basically handling anything that gets in the airspace. So in some climates, there may be a vapor barrier on the inside, on the interior side of the sheathing. That's not that common here where we are, where I am, but I've seen it a few times when I've worked up in the north. So I think that just to understand that concept, these are great. I think the next couple of photos show different views. This is an isometric of the same concept. You see basically what they're calling a waterproof membrane. I'm calling it WRB, but and then you see the flashing behind it, and then that drains to a weep. So I think hopefully you're catching this. Let's keep going. So basically, I think I'm worried about your time. So we've already covered that. So here's a caulk. Caulk is an air barrier. There is a time when caulk is a water barrier, and that's in systems like painted block walls or log cabins. I know y'all don't deal with log cabins much, but people say, what's a barrier wall? EIFS can be a barrier wall, but not all EIFS. Does that make sense to y'all? Exterior insulation finish system. It's I'm hoping that makes sense. EIFS, if you want to take a note and Google it. There's a barrier EIFS and there's a water managed EIFS. Caulk is a water barrier in a barrier EIFS, meaning when I say barrier EIFS or a barrier wall, any barrier wall means that the water barrier is on the exterior. And so in that case, caulk is a water barrier. In every other case, it's an air barrier, but the industry loves to go, let me caulk that up and we'll stop that leak. And we're always sticklers and go, well, that'll only last as long as the caulk lasts. Windows and doors leak, so they must be flashed correctly. And not just under the windows, but at their ends. And so that's what the third bullet's talking about, is end dams to catch water. If water, we'll talk about it in a second. I think, yeah, and then of course, the bottom bullet's really important. If you're looking at a 40-foot wall or a 50-foot wall, sometimes those flashing pieces come in 8-foot, 10-foot lengths. So you're going to have joints, you have lap joints in your flashing that have to be properly treated as well. So let's keep going. I feel like I'm running behind. I feel like, Rick. Let's skip that slide. So this is happens to be the head of a louver. You can see a weep hole there in the brick, but that caulk is probably blocking a weep. That should be open. So I put that's in here just to show how not to do a head flash. Let's keep going. This guy, I got a couple out of sequence, but let's talk about sills, because sills can be places where you get a ton of water into wall assemblies. This happens to be talking about EIFS, but again, the cladding doesn't matter. But you see, window assemblies are fastened often to the structure with the screw that you see there. So, and you've got to have a flashing under that window assembly. So that requires tender loving care and some design details to properly waterproof that the head of that screw assembly, and to get water out from under the window if it leaks, and you need to always figure that it will. Let's go to the next one. This would be the exterior side of a weep assembly. This is a storefront window system. You're going to run into those a lot in commercial. And notice the sealant at the base of the, notice where the sealant is at the base of that sill or that window. That's blocking a weep. The next photo is going to, Rick, you're amazing. The next photo is showing you how it was done correctly. This happens to be a stucco assembly. But you see the weep hole right under the window. That lets water get out. That lets water basically that gets through the window assembly get out right there. And then there's a caulk joint under. If you go right under that horizontal leg, Rick, that's go up right there. There's a caulk joint there, but that weep needs to stay open. But imagine for a second, so you can understand the concept of an end dam. if that weep is just a piece of metal laid down flat, and water can get to the left edge there and run out the side. So I hope you understand, you got to have a vertical piece at the end that you can't see. It's inside the wall, called an end dam, just to basically hold that water in so that it gets out that weep hole. So anyway, let's keep going. This next, and if you look at the left of the picture there, you can see I've got a rough opening and then a sill pan, and you see the left end of that sill pan. If you put your arrow there, Rick, go to that's the back dam. It's a sill pan, so that's flat or slightly sloped to the exterior. And then behind it, it would be right above the word sill pan. You can see that's a back dam. All pan systems under Windows should have a back dam. And then at the left side of that, you can see that's an end dam. So you got go to the far left. And then come up to the flashing. That's the vertical edge. That's the end dam that's going to keep water from running off the edge of the side. And then you can see the corner and then the back dam. Is that making sense? This is out of Gelled Winds. Gelled Wind has some of the nicest details. And I borrowed this from them years ago and love it. So let's keep going. You can screenshot it or go to Gelled Winds website and get some of their details. There's just some good flashing details. The window would sit in the little stone assembly and then be flashed with a back dam. And then that back dam would basically come down the slope section, come down the vertical with a cleat. That's a really nice system. So that's a good photo for you. There's a drip edge in this photo. Might be a good screenshot for you because people are going to use drip edge and flashings and end dams. They're just going to use these terms at BS like you know them. Anyway, that's a pretty good little good detail. Let's keep going. This is a typical construction joint or a control joint in brick. Kind of driving home the point one that you need them. You've got to have those typically about every 30 feet in a brick system. But they leak. So if there's not a good water barrier behind that, that's going to let water through. While we're on that, brick is porous and mortar is super porous. So, in a system like this, you're expecting water to get to the WRB and the air barrier behind that assembly. So let's keep going. Air barrier is really important because I'm going to show you why here in a second. Why free water gets in holes, absolutely, but air gets into walls and into interiors very easily if the WRB and air barrier combined, or if they're separate, doesn't matter, have holes in them. If they let that vapor water to pass, let's say it's I'll use Atlanta. I'm going to use Atlanta as a guide, but if anybody's up north, just reverse the time of year. Let's call it summertime in Atlanta. It's 95 degrees and 95 relative humidity air on the outside. If I've got holes in my air barrier, that air is going to find its way to the hole, migrate into the opening, and then inside I've probably got 70 to 75 degree air with relative humidity of maybe 50%. And air drives from hot to cold and wet to dry. That's basic thermodynamics. So it's going to move. It's going to naturally go that way. If you're up in the north during the winter and it's 70, you got it 70 degrees inside and it's probably 60% relative humidity, maybe 55% relative humidity. And outside is 20 degrees and 15% relative humidity. You're going to have the same thing. You're going to have the water driving moisture-borne water, moisture-borne air driving from the interior to the exterior, finding a hole, and possibly getting into the wall cavity and creating a condensation problem. So
Hey,
this is very
Chris.
important. Yes.
Yeah, we have about a minute left. We
Okay.
need to get wrapped up.
We'll fly through the
Okay.
rest of this.
All right.
So this next slide, you can look up this study. This was done by the Building Science Corporation, buildingscience.org. And this drives home the point. They did this in a cold environment. And they basically measured how much water came through the wall via diffusion. Remember, diffusion is vapor diffusing through a material, and how much came through a hole in the wall, 1 inch square. And during that 6-month period, they had 30 quarts of water through the air via air, and a third of a quart diffused through the material. You can look up buildingscience.org and get hours and hours of what we've been talking about for the last 45 minutes. Let's keep going. So, and so if you got a hole in your wall system or your roof system, wind creates pressure differentials. Pressure differentials may amplify problems. Let's keep going. Stack. Well, this is showing you a couple of ways that air can get in. This happens to be like at a utility penetration through a wall, or like an electrical receptacle, places that we have to have. So you can see there's a lot there. You can screenshot that and study this a little bit. You can see a lot of things. Let's keep going. And then we talked about wind is going to amplify problems. It's going to create a negative on the pot. If you see the wind blowing, it's going to create, it's going to blow in on the side. It might be sucking from the inside at different times, at different seasons. That both of those can be detrimental or problematic. So that's a problem. Let's keep going. Stack effect. You get, how does stack effect affect? Well, elevator shafts in commercial buildings, trash chutes, they go top floor to bottom floor. So you can get unconditioned air in a stack of elevator shafts or other chases inside the building assembly that bring unconditioned air into the conditioned air spaces. So you got to think, there's so many things to think about. We can keep going. That's two different cold climate and warm climate, but basically showing you the same concept, right? Let's keep going. Insulation at ceilings, amazing source of waterborne air getting into an attic space. If you don't have continuous ceiling insulation, it can look like a roof leak, but it's just condensation. I'm running out of time, so I'm going to fly low. Let's keep going. That's with a flash on, and then next photo is with the flash off. It's just showing you an air path, and this happened to be a building here in South Georgia somewhere, and they were like, "We got roof leaks." I went on the roof. The roof was pristine. I said, "You got nothing wrong with the roof," and then we started digging, and I was like, "This." You can see the bad insulation here, but they probably had 30% coverage with insulation. So the 70% was just a hung ceiling with no insulation. You got unconditioned air right above it, conditioned air right below it, and getting condensation all over the place. So the guy he came around after we showed him the roof. I was like, "No, you got to see it." This was great. This was a wall. We thought we had a wall leak from bulk water. Took the drywall off. This is right under a windowsill. So took the drywall off under the windowsill because he said, "My window's leaking." I was like, "Okay." And it was the litigation, and we had the budget to cut the wall. This is exactly what we saw. You see, the insulation had fallen down. You see that little board joint? Go to the next photo, Rick. That's an opening. That's air opening. See, you go back up one and then go back to it. it looks like bulk water because condensation and bulk water look the same. So hopefully you're kind of getting the ideas from what we talked about. I'm gonna go like 2 minutes longer and then we'll quit.
Chris, we got
Yeah.
another seminar starting in like a
Okay.
minute, so we got to wrap it
Well,
up. So
I think hopefully this has given you some good insight as you get started going to BES. I'll look forward to seeing y'all there. Introduce yourself to me, and I'll try to introduce myself to y'all. Thank y'all. Wish you the best.
thank you all. See you in Milwaukee.